So we're going to work through the probability concepts exam for NCEA level 3 for 2016. So starting just with question 1 in this video. A product demonstrator for a confectionery company approaches shoppers and asks them if they would like to taste the product. Of the last 528 female shoppers approached, 288 tasted the product. Of the last 31 male shoppers approached, 14 tasted the product. Suppose one of these shoppers approached by the product demonstrator is selected at random. What is the probability that they tasted the product? So the easiest way to get started on this question is to do a diagram. Which sort of diagram would be the easiest way to represent this information? Well, my advice is always consider a two-way table first, because that's generally the easiest, and then reject that idea if there's some reason why we can't, or why it would be difficult to. So looking at a two-way table, I can show this on a two-way table because I've got two category variables, gender, and I've also got whether they tasted the product. And so I can represent that, and also the fact that I'm given counts. So I'm told in the question how many people are in each of the categories, which means I can easily put those counts, like the 288, into my two-way table. And I'm just going to fill those things in. So 528 female shoppers is going to go down here. And why don't you pause the video now, and I want to see if you can fill in this table yourself and see if you can do this question as well. Only hit play when you either think you've got the answer or if you're stuck. Okay, so let's have a look. What else are we told? Of those 528 female shoppers, 288 tasted the product. So that's going to go female and tasted. And of the last 31 male shoppers approached, so 31 is going to be the total for males, and 14 tasted the product. So 14 were male and tasted the product. So hopefully you got the same numbers as me. Okay, and if they add up along the rows and the columns, you know that it is correct. The question was, what's the probability that someone tasted the product? So we're looking at the total for tasted divided by the grand total. So the total for tasted is 302 out of a total of 559 people. So writing that down, labeling what we're working out, and we can't just put 302. Why is that? What's wrong with that? Well, that's not a probability. Okay, so it's got to be out of something. That would be a count. So it's 302 out of 559, and we can get that as a decimal if we want to, and 0.5403 to 4 significant figures. Okay, on to part 2. How many times as likely is it that a female shopper tasted the product compared to a male shopper? Support your answer with appropriate statistical statements. So that means we've got to calculate it. So let's start by looking at what's the probability that a female shopper tastes the product. That means, and we need to be clear on this, out of just the female shoppers, so out of the 528, what's the probability that they taste the product? So it's 288 out of 528. So we need to write that down as a statement. So probability tasted out of the females. Out of the females. Or you could say tasted given that that customer was a female. So the condition is that it's a female, and that always goes on the right. And that equals 288 out of 528, which equals 0.54 recurring. around 55%. Okay, same thing for the males. So what's the probability that someone who we already know is a male tasted the product? So that's 14 out of the 31 males. So probability tasted given male was 14 out of 31, which equals 0.4516, etc. So we want to know how many times as likely it is among the females than among the males. So the way we do that is we divide. We always divide, and because it's comparing it to among the males, compared to the males, we would call the males the baseline group. And so we're going to divide by the baseline group because it's compared to the males. So dividing them, 0.54 recurring divided by 0.4516, etc. Not rounding yet, equals 1.208 to four significant figures. So writing that down, showing our working, and then writing a conclusion in words. So the question was how many times is likely? Well, a randomly chosen female shopper is about 1.2 times as likely as a randomly chosen male shopper to taste the product. Okay, so we can say about 1.2 because we've already showed how we worked it out up here. So that's in our working, and that's really important. Okay, so if we look at how that was marked, and it says here that for merit, which was the maximum credit for that question, you needed the conditional probabilities compared. So that's like this, and they wanted us to divide it to get 1.2 to determine how many times is likely. 1.2 times is likely. Some people subtracted instead of divided, but when you're comparing conditional probabilities to say how many times is likely something is, we have to divide. Okay, on to part 2. The product demonstrator claims that in general, female shoppers are more likely to taste the product than male shoppers. Discuss why the product demonstrator should be careful about using this data to make this claim. So let's think about where did the data come from? How much can we trust it? So it says that the product demonstrator approached shoppers and asked them if they'd like to taste the product. It doesn't say when they did this or how they chose who they would ask. It said they approached them. And it also says of the last 528 shoppers approached. So that could just mean that it was yesterday evening. It doesn't mean it's a. So the key point here is that we don't have any information to give us confidence that this is a representative sample of male and female shoppers at that supermarket. Okay, so that's the point I'm going to make. We have no information to suggest that this sample of shoppers would be a good representation of all shoppers in general. It simply says they were the last 500, well, basically suggests that the last 559 approached. And so, therefore, we really would need a random sample of shoppers at that supermarket and a sample that represents different times of the day and the week, wouldn't we? To be able to make any inferences or claims about all shoppers. So to support this claim about all shoppers tasting versus not tasting, we'd need a large random sample of all people, all shoppers at the store, taken at different times of the day and week. So key point is that we're not told how the sample was selected. And you could say other things too. Let's have a look at the marking schedule for that question. So they had two types of answers here. So type 1, only one sample. This claim is based only on one sample and is likely we would get different results if factors such as location, time, or the demonstrator were changed. For example, a different person asking, the person who's actually saying, oh, do you want to come and taste this product, might have an effect on people as well. Type 2, male sampling variability. Only a small number of male shoppers were approached, and that was a point that we didn't pick up on before. That's actually a really important point. Because there's only a small number of male shoppers, this means that the probability estimate for tasting the product could be less accurate for them. So it's going to vary more. And if we go back to the information, you can see that there were only 31 male shoppers. And so it's not a very reliable sample size. That percentage among the males could really jump around a bit if we took another sample. Okay, on to part B. At a particular supermarket, 43.4% of shoppers do not have a regular shopping day. For shoppers who do not have a regular shopping day, 28.9% of these shoppers buy most of their groceries for the week on a weekend. For shoppers who do have a regular shopping day, 41.2% of these shoppers buy most of their groceries for the week on a weekend. Without performing any additional calculations, explain why the events has a regular shopping day and buys most of their groceries for the week on the weekend are not independent. Okay, so let's think about what independence means. So when we think about what statistical independence means, if you look at your notes, see what it says. For events to be independent, it means that if one of them happens, it doesn't change the probability that the other happens. For example, flipping a coin and then rolling a dice, they have no effect on each other. So the chance of rolling a 6 on your dice stays the same, stays at 1 out of 6, whether or not you've rolled it, whether or not you've got a tail on the coin. So getting a tail on the coin doesn't change the probability of rolling a 6 on the dice, and that's because they're independent of each other. Okay, not independent, an example of not independent would be having a job, having paid employment and owning a motor vehicle when you're in year 13. If you are in paid employment, that increases the probability that you own a motor vehicle. So those two events are not independent. There is a link between them. So in this one here, I want you to have a think about this. Based on this data here, based on the numbers, does the probability that a shopper buys most of their groceries on a weekend change if they have a regular shopping day? Does it? Well, it does, doesn't it? Because if you look, if they don't have a regular shopping day, that probability is about 29%. If they do have a regular shopping day, it's about 41%. So that's quite a big difference. So let's write that down. So probability they buy most groceries on the weekend, so I'm just going to say most weekend, given that they don't have a regular shopping day, so given no regular shopping day, equals 0.289. Because that's for the shoppers who don't have a regular shopping day, meaning it's out of them. The denominator always goes on the right when you're writing it as a statement. Okay, whereas probability mostly weekend, given that they do have a regular shopping day, equals 0.412. So as these probabilities are different, then we can say that those two events are not independent. So this suggests that these two events are not independent. And I'm just drawing an arrow up to the two events. Saves me the time of writing them out again. So this suggests that these two events shown above are not independent. Okay, so I've got my numbers as evidence, and I've labelled what they mean, and I've also correctly answered they're not independent. If we go to the marking scheme, and it says it's actually only for achieve this one. So full explanation given as to why the two events are not independent without further calculations being performed. And you can see they've got a very similar thing to us. Okay, next question. Part 2. Suppose one of the shoppers at the supermarket is chosen at random. Calculate the probability that this shopper buys most of the groceries for the week on a weekday. So let's go back to the information that they've given to us and always think, okay, which is a diagram going to help? And it is. And the first thing you want to ask is, can we just get away with a two-way table like we did before back in question 1? And we could do that in question 1 because they gave us the numbers. They gave us how many people were in the groups. Can we do that here? Well, the answer is no, we can't. Well, not easily. Two-way table is not going to be easy to do. What do you think that is? Well, here's the problem. Where would you put the 0.289 here? Well, because it's not out of everyone. Who's it out of? It's out of the shoppers who do not have a regular shopping day. Now, when you've got conditional probabilities, we cannot display them on a two-way table. We have to do some more calculations in order to do that. And that's going to take a while. So, short answer is when you're given conditional probabilities and not just probabilities out of the total, you're best usually to consider a tree diagram. Regular shopping day, so regular day or no regular day. And then of those on a regular day, we're told 41.2% buy most of their groceries on the weekend. So mostly weekend or not. And then again, amongst those with no regular shopping day, same categories, mostly weekend or not. Okay, in terms of getting these the right way around, if you try it both ways, you'll soon realise which is the correct way. And the key thing is that those conditional probabilities always go on the second set of branches. That's these ones here. And so that's how we know which way around it goes. So we know that of those who do not have a regular shopping day, 28.9% buy most of the groceries on the weekend. So that's got to be here. It's got to go 0.289. Okay, so I want you to pause the video and see if you can copy and complete this table by filling in the probabilities on the rest of the branches. On a tree diagram, by the way, don't put percentages ever. Always put decimals or fractions, because when we go to multiply them, if they're written as percentages, that's not going to work. They need to be written as decimals or fractions. Okay, so pause the video and have a go. Okay, so we know that 43.4% of shoppers do not have a regular shopping day. So 0.434. And what else? We know that 41.2% of shoppers who do have a regular shopping day buy most of their groceries for the weekend, or on the weekend, so 41.2, 0.412, and then we can calculate the rest. We know that each pair of branches has to add to 1. So to get this one here, we're going to go 1 minus 0.434, and 0.566 was the answer. And similarly for the other sets of branches, to find this branch here, we're going to go 1 minus 0.412, because each pair of branches needs to add up to 1. So 0.588. Okay, so now once we've filled in all those branches, probabilities, we can now reread the question and check what we need to do. So calculate the probability that this shopper buys most of their groceries for the week on a weekday. So that means not on a weekend, right? So that means we need to work out this outcome and this outcome. And it's a really good idea to tick the ones you want to work out. So probability of being on a weekday is going to be probability regular and weekday, and plus the probability of not regular and weekday. So that means for regular and weekday, we're going to be multiplying along these set of branches here. So equals 0.332808. And then same thing for the not regular people who shop on a weekday. So 0.434 times 0.711, and we get 0.308574. And then to get the total probability of someone shopping on the weekday, doing most of their shopping on a weekday, what do? Well, we add those probabilities, which equals 0.6414 to 4 significant figures. Cool. And we've got our diagram, we've got our working, and we've got our answer, and we've labelled it. Part 3. Suppose 3 shoppers at the supermarket are chosen at random. Part 3. Suppose 3 shoppers at the supermarket are chosen at random. Calculate the probability that all 3 shoppers have a regular shopping day and buy most of their groceries for the week on a weekend. And it says support your answer with statistical statements and reasoning, including any assumptions made. So when it talks about assumptions, it means that there are assumptions. You've got to talk about those. And so you don't forget to talk about them, it's a good idea to circle that at the start, because people often forget to and miss out on credit. Okay, so what do? If it's asked for all 3 shoppers, you start with 1 shopper. So for 1 shopper, the probability that that shopper has a regular shopping day and buys most groceries on the weekend, so regular and weekend. Remember that symbol means and if we go up to our tree diagram, so that's just going to be going along regular times probability mostly weekend. So 0.566 times 0.412. And here we go, and the answer is 0.233192. We won't round that yet because we're not finished. Okay, so we've got that written down and we've labelled what we're doing. Okay, so for 3 shoppers, probability that all 3 are regular and weekend. So what we do is we multiply by itself. So for 2 shoppers, it'll be 0.233192 times itself. For 3 shoppers, it's times itself again. So it's going to be 0.233192 to the power of 3. And we get this number here. So 0, we can round it now because it's the end. So 0.01268 to 4 significant figures. Okay. Okay, now what assumptions are we making here? So there's 2 that I can think of. I want you to pause the video and have a bit of a think about it yourself. Well, the first assumption that I can think of is that we're assuming independence of the 3 shoppers. Whenever you multiply probabilities to get the chance of those events both happening, or in this case all 3 happening, you're having to assume that those events have no influence on each other. So this assumes that whether each of these three customers has a regular shopping day and buys their groceries on the weekend is independent between these three shoppers. In other words, that they have no influence on each other's shopping behaviours there in that way. And it's probably a reasonable assumption. Why? Well, it's reasonable, I think, because we're told that the three shoppers are chosen at random. And as long as we're dealing with a large sample of shoppers, that's probably okay. So we're not just taking the three shoppers in a row. I mean, three shoppers that shop at the same time of day, they may not be independent, because the same sorts of age groups, gender may shop at similar times of day, for example. So this is probably reasonable because we're told they were chosen at random. And the second assumption I could think of was that we're assuming that it's a large sample, because if you have a small sample of, say there was only 50 shoppers, when you choose one, it means there's only 49 left, and so that changes the probability slightly, doesn't it? If you have 1,000 shoppers and you choose one, it doesn't change them much noticeably at all, because it just goes down to 999. So, like, for example, if you look at 23% roundabout of shoppers shop regularly and on the weekend, mostly on the weekend, out of 100, then when you chose one, there'd be only 22 out of 99 left. 230 out of 1,000, there'd still be 229 out of 999 left. Not much difference. So it wouldn't affect things much. So the other assumption is that we're assuming the sample is very large. My technology stopped working, so I'm just going to read this part out. So we're assuming the sample is very large, so that it makes no difference, or makes little difference, whether we sample with replacement, meaning we could get the same person twice, or without replacement. Okay? Right, marking scheme. And it won't let me zoom in anymore, unfortunately, either, so I'm just going to have to squint really hard at the screen. The key thing was this was actually an excellence question, and it was excellence if you correctly calculated the probability for all three shoppers, and mentioned one assumption that you stated it clearly and in context, so you didn't have to get both. Merit was if you got the correct probability, but not the assumption, or if the assumption wasn't clear. And achieved if you just got one correct probability for one shopper. And you can see the model answers they've got there. They're the same ones that we came up with. Okay, I'll do another video for question 2. Ciao.